Okay, everybody. We have here Coughlan. He's an expert in communication methods and business development. He's well known for building bridges between commercial and non-commercial stakeholders in the technology sector, and he will speak to us about the OpenRelief team, and how using open source software and open hardware tools, they build disaster relief tools, disasters such as earthquakes, weather disasters, radiation disasters. Okay, so let's welcome him.
Well, ladies and gentlemen, can you hear me clearly? No problems there. So today I'm going to give you a bit of a lightning tour of a project that's trying to integrate hardware, software, and management processes to solve a very specific problem. As you're probably well aware, we have quite a few disasters around the world every year. Quite a few of those are serious. And disaster relief efforts to respond are often extremely hard to arrange. Basically, disaster relief is trying to peer through fog. Something large happens, and you have to go in there and try to work out how big was it, how much is damaged, how many people are in trouble, and how to get help to them as quickly as possible. OpenRelief as a project was particularly inspired by the 2011 Tohoku tsunami and earthquake in Japan, where we had the unfortunate incident of losing approximately 500 kilometers of coastline. Water came inland up to 10 kilometers at points, and we had over 100,000 people displaced, with 20,000 dead. That type of incident really graphically illustrates how, as far as technology has come, as small as the world is today, how we can be badly stranded and confused when nature strikes. Now, OpenRelief is a project to try to plug some of the gaps. It's trying to develop tools to help people respond more quickly. In particular, we're trying to solve the problem of understanding what just happened, clearing the fog a little bit, so disaster relief can be quicker. Again, a good illustration is the Tohoku disaster, where it took almost 2 weeks before we had a clear understanding of the geography and human situation inside the disaster zone. The roads were gone, infrastructure was gone, we had people displaced, we had people dead, we had people quite simply missing that turned up in different areas. It took a very long time to get the ducks in a row so that we could do things like get food, medicine, and other provisions to people in the quantities needed. Even though, to give you perspective, Tohoku was about 3 hours drive from Tokyo, when I visited on one of the relief drives 1.5 weeks into the disaster, in some areas people were still on quite strict rations. We simply didn't have the logistics and the understanding of how to get the things to people quickly enough. OpenRelief, well, we're trying to deal with that. What we're trying to do is we're trying to get information to disaster relief first responders a lot more quickly than we could in the past. And the purpose for this is really simple. We want to get the right aid to the right people at the right time. We want to avoid situations, which do happen in reality, where you have trucks of provisions going into a disaster zone, arriving at a shelter where you have hundreds of people who just had a similar delivery a few hours ago. The truck then has to go all the way out of the disaster zone and wait for reassignment. Meanwhile, somewhere else, people are hungry, people are cold, people need medicine. This is a very serious issue. It's something that OpenRelief is going to contribute slightly towards. Of course, we can't solve this problem, but we might be able to reduce the amount of waste and time lost. The first step is what we will cover in some detail today. The first step is reconnaissance. This was a big issue in Japan. At one point, we were having a meeting with multiple NGOs. We had triage doctors going into the disaster zone, and we had a question about a particular village on a peninsula. We were unable to find out if that village existed, if the people from the village were still there in any quantity, if they needed provisions, or had they been moved elsewhere. The village was 40 kilometers away from where we were, but to get there took over 4 hours. If we had had the ability to do quick reconnaissance, we could have had that task accomplished in less than an hour. As it happened, that particular village was fine. The military had pushed through. Provisions had been sent from another area. They did not need help. It was a wasted trip. We want to be able to do quick reconnaissance and mapping to reduce that type of waste, and we want to introduce a way to do that that is in some ways revolutionary, a drone, but in other ways very accessible. The technology we want to use to accomplish this, we want it to be something that is available to everyone around the world at extremely low costs. I'm going to explain that to you now in a little bit of detail. First of all, let's start with the requirements. So the basic requirements are fairly simple. We need something that disaster responders can bring into a disaster zone and just put down and launch almost anywhere. So basically it needs to take off from footpaths. It needs to have the capability, where possible, to automatically recognize roads, people, and things like smoke, so you understand what is happening in a disaster zone. It needs to photograph, film, and map the landscape so that disaster response teams can have quick analysis of the situation. And it needs to, where possible, measure the weather, radiation, and other things that might affect your disaster response. In Japan, as you'll be well aware, that was particularly important because of the Fukushima Daiichi triple reactor explosion and the subsequent concerns about where the radiation clouds were heading and in what quantities. So we have a pretty broad mandate for what we want to do, but we found a lot of the things, well, quite frankly, they were already ready. Here is OpenCV running in an early version of our code. It's recognizing roads here from photographs. Here it is recognizing people, a very important thing for working out who's on the ground. And then it's going to show you in a second what I think is one of the very cool parts of the technology. It's recognizing smoke here. Imperfectly, but it's getting smarter. We're adding flame recognition as well, which allows you to have a pretty good idea of danger points on the ground. That is OpenCV with a bit of custom coding, very small amount of custom coding, and a little bit of training. The extra bits we've added, we are, of course, releasing online so everyone can integrate them. But it was surprising how some of our, what you could say, more difficult requests, recognize people on the ground, turned out to be fairly easy to accomplish. A lot of that work had already been done. The plane had not been done, and that's where we had to put quite a bit of time and thinking into it. So the idea here was that this technology would be accessible all over the world without having to rely on a single provider. OpenRelief itself is a design project. We have no intention of building and distributing the technology. We're designing it. We want everyone else to be able to build it, either commercially or non-commercially. So off-the-shelf components, open hardware where possible so that you can machine it wherever you are, and open source and free software wherever possible as well, so that the code to run the thing, the code to recognize people, the code to communicate the results, that's accessible to everyone without any fees, without any barriers. The first steps, essentially, were very simple. Lots of glue, fiberglass, balsa wood. Basically, the technology is extremely primitive, and our first prototypes were large RC airframes. We built two prototypes, one for the UK and one for Japan. You can see them on the floor there being put together. They're about 2 meters wide. These prototypes were essentially fiberglass over balsa wood with some metallic elements. And well, they kind of worked. Here is the Japanese drone hanging around a lunar eclipse a few months ago. It was painted red simply for visibility and because that matched the Japanese disaster response colors. The thing is, the first airframe, it was out of materials that you can get anywhere. So it's fiberglass, it's balsa wood, it's 1.6 meters wide, it's about 1.2 meters long. The weight is very, very low. It's only 2 to 3 kilos, depending on how you set it up. And it can have 20 to 30 minutes endurance. It's not very fast, so 20 to 30 minutes endurance translates into somewhere around 12 to maximum 30 kilometers if you're able to glide and so on, not just use power all the time. As I said, it kind of worked. This first airframe allowed us to have proof of concept that you can build a drone at very low costs. It was pretty fragile, the range was pretty low, and quite frankly, it was pretty easy to break and quite hard to fix. But the important point I put in here is that we managed to build that airframe with the AutoPilot, the computer, the engines, the batteries, all of that for approximately $740 per unit, which changes the game in drones completely. Before, you'd have to spend around $12,000 to have comparable ability. So $740, because we used off-the-shelf, open hardware, and open source software. Kind of worked, kind of worked. Phase 2, of course, is to take the kind of work and start to turn it into something that can really be used in the real world. We were actually helped out here from the other side of drones, the kind of the military-industrial complex. We were contacted by a UK aeronautical engineer and head of a UK company that is working on a commercial vertical takeoff and landing drone technology. This vertical takeoff and landing drone technology is very small, very capable, and I suppose eventually will be a very expensive solution for militaries around the world to have vertical takeoff and landing with horizontal flight at up to 240 kilometers an hour. Anyway, that company, as part of their development process, had built this, a prototype conventional airframe to test some of the principles, like the counter-rotating propellers to prevent torque and increase stability. And they contacted us and said, your airframe is off the shelf. This airframe is fully designed with CAD. We're not going to sell it. How would you like it? So this became what I believe is actually the world's first open source airframe. They gave us all the CAD drawings, all the technology on this, and the head of the company is helping us further develop it. So this particular airframe, I'm going to dive into it a bit, is very similar to the first. It's aluminium, it's wood, it's 1.8 meters wide, 1.4 meters long. It weighs 3 kilos or so. It has 12 kilos of thrust, which is an awful lot of thrust given the weight. It can fly 4 hours on electric if you load it with batteries. It can do about 10 hours on gasoline, and it can fly at about 160 kilometers an hour. So basically, this airframe is very light, very small, very capable. It can carry about 9 kilos of cargo as needed, and it can fly for up to 10 hours or 1,000 kilometers. So that particular airframe has very advanced features, even though it looks very simple. The counter-rotating propellers I mentioned before, they help prevent the airframe having instability in flight, like torque shake, so that your camera stays stable and recognizing people on the ground is easier. It has a variable center of gravity. The wing, actually, the main wing moves to change the center of gravity of the aircraft depending on cargo, so that when it's flying light, it's extremely stable. When it's flying heavy, it's extremely stable. That type of very simple technology is a revolution for these small aircraft. We haven't had that before. It has channels on it, like a movie camera, so that you can clip things on, whatever is needed, to reconfigure the airframe into new uses, whether you need it to have conventional landing, whether you need it to land on water, whether you want it to fly into nets. You can change the outer configuration of the airframe as required. It has a large cargo space in the fuselage. As Eddie, the designer, said, it is basically a 3 2-liter cola bottle cargo space. It will hold 3 2-liter cola bottles down the cargo space. So you can load it up with whatever you need. If you need to send something over the horizon to people you can't get to, you can do that. You can do that up to 9 kilos of weight. And as I said, it can be reconfigured. So it can launch by rails. It can launch conventionally. It can go off water. It doesn't matter. You can reconfigure it into any shape you want because of the external rails along the fuselage. I have some photos of what it is because I think it's very cool. This is what we got, the prototype, the counter-rotating propeller engine. This is the rail system with the body being put together in 3 sections. These are the electronic speed controls to cool down with air the engine components. It has got the cargo space displayed there. You can see the main fuselage in one piece with the adjustable wing right there. The first version of it displayed here, and at the Open Source Hardware Summit a couple of months ago, that's Eddie in white, showing a slightly more advanced version of the airframe. Little details on it, again, quite revolutionary. You might be able to see on the tail. Do you see 2 black parts on the tail there? Those are the servos to control the flaps and so on the aircraft. Each control surface has 2 servos. so that when one fails, the aircraft does not fail. We're going to have a very simple method to prevent the servos kicking each other out by having a slight zigzag in the wire, using the wire that the servos use. So even if they go slightly out of sync, they don't stress each other. In essence, what it means is this very simple airframe, which you can fly and rebuild if you have a hammer, a screwdriver, and a wrench. It has advanced features so that even if it loses servos, it doesn't go out of the sky. Even if you need to reconfigure it with a lot of weight, that's no problem. If you need to rebuild it, you can get plastic piping for the fuselage. It's an extremely flexible solution, and it comes out of a sort of an area where they need that, because naturally with military technologies, they don't always have optimal conditions. This is built for that type of arena, and we were given it. We were given it and we put it out there. So we've released it under an open hardware license, and you can download it at that link. This airframe, I'll be frank with you, it's under development. I'm going to get to our milestones in a second and explain the release date. So the CAD files you'll get there are of the first generation of the airframe that you saw Eddie with on stage. We found some issues with it already, like the tail broke. It got knocked off a stand in wind and the tail broke. So we redesigned the tail. Eddie created a new design for the tail where each segment of the tail is precisely the same. So you only need one replacement part for all three sections of the tail, and it's much stronger. Anyway, first version there, second version coming soon with improved design. Very simple, very interesting technology, huge range, game changer. Again, it only costs less than $1,000 to buy. Let's dig into it a bit more. The details. What is this stuff really, apart from aspiration? Well, we use what's called the ArduPilot to fly the plane. If you're aware of drone technology in the amateur market, you'll know the DIY drones community. They made an autopilot that's extremely capable. I'll run through the features in a second. The camera, well, the camera, you can either go really expensive or you can go really cheap. We went really cheap. We're using a super HAD camera from Sony. The camera cost $41 from China with a full lens build. And I'm going to explain the details in a second, but basically it's a door peephole camera. And it gave us enough resolution to see people at about 10 kilometers. That was pretty cool. Arduino-based sensors throughout, easy to program, very cheap, easy to obtain. Raspberry Pi to process data as what we call the minimum. Naturally, we're also playing with things like Tegra 2 and Tegra 3 boards. But yeah, Raspberry Pi is your basic starting point on computation here. And a Linux-based OS to analyze the data. Digging in. So the AutoPilot. How many of you are familiar with autopilots? Zero in the room. One guy there. A little bit. Well, this one's interesting because I bought this one at $300 and they just released a new version at $200 with a lot more features, and it's a lot better. The autopilot market has completely changed in the last couple of years. This particular autopilot, the ArduPilot, is completely open source software and open hardware. Everything about it is released under schematics and code. This means that you can simply build it yourself, if you're that insistent on playing with diodes, or you can buy it for $200. It's got a very simple 80 mega processor. It's got the very small amount of RAM. It's a very basic chipset, but it allows you 600 3D waypoints. It's able to reboot in midair. It's got a black box. If the system goes down, you can work out what happened. It's got the type of features that were completely inconceivable at a $200 price point just 5 years ago. That's what we use as the brain to fly the airframe. And this brain is extremely capable. It can be repurposed for land. It can be repurposed for water. It doesn't matter. It already has different forms of the code that you flash onto it for other use cases if you happen to need them. The camera spec, I mentioned it's a door camera from China with the lens and the build, and the sensor is from Sony. It's a very simple camera, but you'll notice on the specs, it's extremely capable. I mean, f1.2, it can operate in pretty low light indeed. It's got resolution which is just above television, so we can get everything we need for the OpenCV to recognize things like people and roads. And it is able to take a lot of temperature variance. So when you're storing it and so on, you needn't worry that you're going to lose resolution on the camera because the lens will fog up or whatever. It's a very versatile solution, and like I say, it only costs $41 off AliExpress.com. That's where we got it. Very cool technology, just a door camera that was overbuilt. Computer, Raspberry Pi. Now these specs are out of date because I read that Raspberry Pi is going to have 512 megabytes of RAM from now on. The ones we were playing with, 256 megabytes of RAM. Raspberry Pi is a really underpowered computer, but it's plenty to connect to the AutoPilot and do some of the computational tasks we would want. So, for example, with the OpenCV, the visual recognition, it can do some of the recognition as it flies. It can't do all the detailed analysis, but it can do some of it in the air. It's a very cool, very cheap solution, about $30 to get this done. And what's useful for us was that this particular platform, while being exceptionally cheap, was also very easy for people to program for, with quite a few Linux-based distros being put onto it and quite a quick community growing around it. Very accessible technology. Software, the AutoPilot is ArduPilot. We were using 2.32. Basically, the operating system, as long as it's Linux-based, it doesn't matter what you're using. A lot of the Raspberry Pi stuff is sort of Debian ecosystem-based, but it doesn't matter. You can put anything on there. OpenCV 2.3.1 is what we used for the first systems. That code is already released online where we've done custom code, very basic. The custom code for smoke, people, and roads. We're also working on structure from motion where you build 3D maps out of the camera images. All of that just goes online. We're trying to upstream what we can. What we haven't upstreamed yet, it's just in our repositories. Very simple software. Outside the plane, the aircraft is very capable. It can do all kinds of interesting things like mapping and carrying cargo, but it's useless in some other aspects, like a plane trying to tell you what the weather is like on the ground or the radiation on the ground. Not going to happen. So we had to think through that problem. We wanted to understand what the pollution was, what the danger was in disaster zones. So we also needed to think about sensors. Now, probably everyone in this room knows that the open source hardware, open source software community has been building things like radiation sensors, Geiger counters for people, especially in the aftermath of the Japanese crisis. We looked at some of those, and we didn't find anything that was suitable for us, because we were looking at a situation where some of the technology would have to be left in the ground, out there, reading for up to weeks at a time. The Geiger counters that are available usually consume a lot of power. And in many cases, they're not built for networking. So we had to think through that problem, and sort of to play with it, one of our guys built a radiation sensor that can transmit data to the drone, and that can be used to make your geographical information map of the disaster. The radiation sensor, I think it's pretty cool. It's a nanode board, very simple technology, 80 mega again, that chip keeps cropping up. We used a custom ionization chamber for our test system, and our particular custom ionization sensor, it's very similar to a smoke detector. It doesn't draw any power, it just uses a reference charge. So the only power being drawn is for the nanode to get readings. That has the interesting result that you're able to leave the sensor for a very long time out there getting data. Here is the actual first radiation sensor, built in what's basically a jam jar because our engineer had a sense of humor. Very basic stuff, just a very simple ionization chamber. There's the reference charge from the battery stack, and there's the connected device with the nanode, the chamber, and the batteries, built by this chap, a complete lunatic, ex-British telecom engineer called Andrew Back, who splits his time between steam-powered technology, essentially, and stuff like this. He combined it to make this radiation sensor. Total cost of that radiation sensor is crazy cheap. A nanode is something like $18. The chamber is any chamber with metallic elements, and it would come to about $20 per radiation sensor. The radiation sensor, of course, can broadcast in the air about half a kilometer, and it can also broadcast over the LAN cable if necessary, if you're at a fixed infrastructure point and you've got that capability. Very cool technology, very simple, very cheap. Putting it all together, the vision here is that you would have a disaster relief headquarters, you would have sensors on the ground, and you'd have the drones picking up information on their own and from the sensors to give you a fairly complete map of a disaster zone at very low cost. You could have one drone, you could have 10, you could have 100. What we want to do is have something that basically allows you to have as elaborate a disaster relief response as you need. So putting it together, the basic thing that you need is a mission control. Again, that problem, fascinatingly enough, was almost completely solved. The amateur drone community had most of the components in place. So a laptop, a Linux distribution or Windows or Mac, it really doesn't matter. Running something like Mission Planner from the ArduPilot community, the DIY drones community, that allows you to put on the waypoints for the drones to take off and fly themselves and return home. VLC player for things like your video footage, and then having normal disaster management software such as Sahana Eden. Sahana Eden, in case you're not familiar with it, came out of the 2003 tsunami. It's used by organizations like the Red Cross for disaster response. It's very large, quite complex software that allows you to deal with all of your logistics, your GIS mapping of disaster zones, and information reports. Our goal would not be to build new technology where we could integrate into existing technology like that. In essence, you'll have gathered the drones and the sensors create GIS data. They would pour that into something like Sahana Eden, and it would integrate with all the other GIS data that disaster relief teams have to increase their response time. So the three cool things here, the reason that this is useful is that the GIS data going into existing disaster relief gives a more complete picture of the disaster zone. It simply adds a greater granularity to what you're seeing, what you understand has happened, and that means your response is better. We're building it to hook into OpenStreetMap with the interesting consequence, given that this can recognize roads, that we can rebuild OpenStreetMap maps in a disaster zone to let people know where the new roads are, much faster than ever before. We're still mapping on the ground the Japanese disaster zone for OpenStreetMap to try and get a picture of where the new roads are. It's taken more than a year. With this type of technology, we'd hope to reduce that time dramatically, at least for major arteries that the planes could easily see. This technology is not designed to stand alone. It's designed to be part of something bigger, to integrate into existing processes. We're aiming not to have any not invented here syndrome. We don't want to do anything special to replace any existing technology. We want to fit into the existing technology and expand the capability where possible. So we want to work alongside OpenStreetMap, we want to work alongside Sahana Eden, and indeed we are. Currently we're in discussion with the Sahana Eden Foundation, the Sahana Foundation I should say, deciding how much of our technology will be built standalone and how much will be integrated in plugins to their disaster management for maximum efficiency, while also allowing people to use other disaster management technology where required. Milestones are fairly aggressive. Will we hit the final one? December of this year, we hope to have the fundamental technology production ready. The airframe, it looks like we're there. The airframe is coming along very nicely. The software, well, we're getting there. A lot of the individual components, like loading up missions, taking missions off the planes, and getting it into things like Sahana Eden, it's coming along well. It still looks good for December. We are not necessarily gluing it all together as prettily as we could, so we might not have something that's beautifully production ready by December 2012. And quite frankly, we don't really care. What we want to do is get this right. Now, the reason our target is so aggressive is because the longer we don't have it ready, the more that we look at disasters, we see things happening, and we think we should be able to help solve that. But yeah, that's our target, December 2012. If we're ready then, awesome. If we're not, we'll keep trying. We want to get it right. The idea here is crowdsourcing. OpenRelief is a project. Basically, it's a group of people who have a common goal of improving our disaster response based on the technologies that we have knowledge of. Lots of different stakeholders, aeronautical engineers, software people, AutoPilot people, whatever. It's a community. Because we're crowdsourcing and working on a non-commercial goal together, we're able to get quite a lot done quite quickly. We're looking for more people to join in. Everyone is welcome. The idea is to build a community around the world that, where possible, turns the potential of these technologies into solutions for disaster relief and does it as well as possible. So, We're quite global already. We have people in the US, the UK, we have people in Singapore, we have people in Japan, obviously, and Australia working on this technology. We want to be able to get people all over the place to send us their requirements and to help us brainstorm the problems to get things working. We have a little ecosystem. A bunch of companies are already contributing technology, time, even on some occasions resources to get things done. So my own company, OpenDawn, underwrote the cost of building the first 2 prototype drones. CodeThink made sure that we had some engineering time to get the drones completed. We had Toradex in Switzerland helping to donate computers, in this case Tegra 2 computers, for advanced testing of on Airframe technologies. Nanode, of course, gave us the nanodes for the radiation sensor. And that little model shop, Phil's model shop, gave us the wires we needed to complete the drones when we were stuck. So this little community, it's just starting. We need more people. We need technologists to help us build the technologies and refine them. There's a lot of areas where we don't have the necessary expertise yet, or we don't have enough of it because we're all professionals and our time is limited. We want disaster relief workers to help give us context and make sure that we are focused on getting realistic solutions and not just play with technology and engineering coolness. And we want commercial enterprises to eventually put some of this technology into production. We're actually talking about the first OpenRelief product, you could call it, where a commercial enterprise is looking at making the radiation sensor either sometime this year or next year, in which case it would be available for order for anyone around the world at a pretty modest price. So we do need people, seriously. We very much need you, and we have some areas in particular where I thought coming to this conference would be useful. Quite frankly, we've got a really cool airframe. I think nothing comes close to our airframe in the world for this price point with this capability. Absolutely nothing. And we've got the basic tools to accomplish the tasks. We were able to put the plane in the air, take it back, and we're just about ready to send all the geographical information data into disaster management. But integration is really a problem for us. Let me illustrate this graphically because it's embarrassing and it's true. So we began drawing lines to discuss our integration and how we could have what we called, at the moment, the drone manager to tie together the various software tools and make it easy for us to basically make a mission, send it to a plane, download the mission from a plane, and put it in disaster management. And we started doing lots of this, talking about RESTful interfaces and what different tools would work where. And second iteration, we ended up with lots more lines. And at that point, quite a lot of our volunteers who aren't hardcore kind of, passed out. And what we have is a situation where we have immensely cool technology that does need a little bit of glue to tie it together effectively. And we do need smart engineers to help us get that glue right, because we are stuck at having big diagrams, and we could really do with a hand on this to make it a lot simpler. I know it can be a lot simpler. It's just that this is all of the stuff we need to do. These are all of the tools we need to use. We must find a way to put them together sensibly in modules that everyone can understand and further customize or further develop as needed. Okay, so be part of this. That's my message. We are here at OpenRelief.org. We have a little website. We have mailing lists and so on. Join our developer list to get up to speed. If you want to help us communicate the message of this technology, join the outreach list. We're doing our best to do as much as we can within the context of our day jobs, because all of us are volunteers. So, for example, my true moment of shame is that essentially for 2 months, I personally had very little time to contribute to OpenRelief because for my day job, I was traveling incessantly. I simply had no free time. And it's the same for everyone. Everyone thinks this type of technology is useful. Everyone is trying really hard to get it finished, but we don't have enough manpower on a volunteer basis to do it easily and to do it as quickly as we want. So if you have knowledge of software or hardware or both, and you think you could help, please do. You'd be very welcome. We're a really open and friendly community, and we really like to work with people. Getting our tools, getting our code, it's really simple. We try to put everything out basically as we get it done. Sometimes, like for instance, we have one programmer in New Zealand who's really busy on his day job too. He's doing a lot of the OpenCV stuff. And sometimes it takes a while for the new code to find its way into our repositories. But basically, whenever we get something finished, we try and push it out. So you can get our software code on Gitorius. You can find some of our electronic schematics, like the radiation detector, on SolderPad, which is an open hardware website. And you can get our Airframe currently on our normal website. We're looking for a repository that would be managed for this type of physical open hardware that would be suitable to place these things on in the future. If you have suggestions, let me know. So stay informed. We went all social media on this to try and share the message outward, because we're very aware that the actual target audience for these technologies are not technologists. The target audience would be disaster responders, people who can use the technology in the field. So we want to try and ensure that we have a continuous dialogue about what's being built and why. So we use Facebook, Twitter, and Pinterest. Pinterest you might like to visit just to see all the airframes. We've got tons and tons of photo of the build processes and the testing and so on there. Do have a look. And, perhaps most importantly, do contact us. If you're not quite ready to jump into our development list, contact me. There's my email address for OpenRelief. I'm very happy indeed to speak with anyone about any part of our project and to help understand what you could bring to our community and how I can ensure that you get rolling on what you're good at as quickly as possible. Like I said, we're very inclusive, we're very open, we're not dogmatic. We are doing this because we think a lot of the open hardware and open source software available in this area can help save lives. And we can do that as a contribution of professionals in this field in a productive way, in a very short time scale, if we collaborate. So our whole community, the idea is we're trying to get technology out there to help people, to save people. Everyone is very welcome to join in. We really do need your help, especially on software. And that's essentially it for the formal part of the talk, though I'm very happy to take questions, which you may have a couple of. So, ooh. So, any questions? There's a gentleman in a green top.
I do know that you mentioned that OpenDawn, your company, was funding the initiative, but yeah. I was just curious where the funding was coming from, if that's disclosed to open source
for the
financials, yeah, that the money's coming in.
Oh, well, there's been very little money spent. I put about $5,000 US into the project to buy the equipment and to get things arranged for the first 2 prototypes. But apart from that, and the donation of hardware by Toradex and Nanode and so on, it's just been time for people. Now, what we are doing with an eye to the future is we are setting up a legal entity to basically have responsibility for the project, because we do think that further down the line there'll be more prototyping needed, and that will require financial investment again. So we're going to set up essentially an association which can accept money and spend it on the project. But right now it was just the first few people in the project put money into it to get things done. So yeah, my company put in about $5,000 to build the first airframes, AutoPilots, and to pay for costs like showing at the first events. As I say, Toradex donated some computers. We had some donations from Nanode, and the guy Eddie Strickland, who built the advanced airframe, also put money into it to finish the airframe prototype. But we're doing that as basically part of our, you'd call it charity outreach. I mean, it's like this is money that we would donate into something like the Red Cross. We're donating it in here. And there will be a formal legal entity set up for the future for funds.
Okay, it's great for a proof of concept. I was just, so in the future you think it'll be donation based, that people will give to OpenRelief, and then you'll be able to make planes and other reconnaissance tools and such?
OpenRelief will not make anything. It's a design project, so it will create designs and release them. What we will try and do is encourage commercial entities to produce technology and sell it in the market. And of course, we want to release everything as open software, open hardware, so everyone can make it if they want. But we don't envision OpenRelief being a producer in any shape or form. So OpenRelief is a design project. It's simply going to design and refine the technology based on knowledge donations. Getting into production of this technology would be too difficult, too costly, and too much of a liability. This is stuff that is going to have an awful lot of variables. You know, the airframes alone, the variables of flying them, repairing them, warranty. We couldn't do this on a volunteer basis. It would be inconceivable. And we have no interest in setting up an OpenRelief company for doing this. Now, we do have an interest in encouraging companies to commercialize the technology, but OpenRelief will only design and release the designs. It's intended to be a place where we can get knowledge from all different areas, combine it into disaster relief, and put that out there so that people can use it. Because we're at an interesting point where we can have intensely effective solutions for problems that we couldn't have done a few years ago if we get the right people in the right place sharing information. Once we do that, it's mission accomplished.
Thank you.
You're very welcome. Any other questions? Gentleman over there.
Okay, you said you're interested in companies to build your stuff, but shouldn't governments be also interested in this and being responsible for reliefs of disasters? Do you get any interest from governments, or have you seen interest from Japan or UK?
It's a good question. There has been no formal expression of interest. Informally, there is a slight degree of horror from strict bureaucracies with this type of technology. So, for example, in Japan, virtually everything about the airframe and the communication technology is illegal, because we have just gone way past all of the known boundaries and built something that's completely over the horizon of what they're legislating for. So it's very difficult for them to work out what to do with this. I mean, the airframe we have now is extremely capable. I mean, it flies at 160 kilometers an hour. It can do 1,000-kilometer runs. It's very small, very portable, very light, can hold 9 kilos of cargo. It's insane technology. And then it's got an AutoPilot that allows it to fly at 600 three-dimensional waypoints, which allows it to do all kinds of crazy things if you wanted it to. Basically, we're just off the reservation as far as bureaucracies are concerned. So we probably won't see governmental buy-in to this technology in the first stage. What we will see is disaster relief. So, for example, I'm speaking with Team Rubicon, a veteran association for disaster relief in the United States, and they responded to things like the New Orleans disaster and so on. They try to get out there and help normal emergency services. And they come from the military, so they're very well aware of things like drones. And those are what you'd call early adopters that are looking at this technology. And because they're very well known on emergency relief, they're the ones that will help with getting governments to green light the technology. In Japan, we're trying to work with OpenStreetMap Foundation Japan. Once we have an airframe that we believe is out of alpha crazy testing, we want to try and get it in the air in cooperation with OpenStreetMap Foundation Japan and perhaps a university or two in the disaster zone, perhaps even in the radiation exclusion zone, so if and when it crashes it won't do any particular damage. That will be a process of essentially partnerships. So working directly with governments is not what we're aiming at because they're very bureaucratic. Working with responders is, and commercial entities which are eyeing the horizon of 3 to 5 years in the future when governments get this and suddenly say, yeah, it's a good idea to have 1,000 emergency relief drones that can quickly map a disaster zone. Or another illustrative example, in Japan we lost the East Coast radiation sensors in 2011. It went dark. What we knew was something was coming. We didn't know how big. We didn't know how fast. So there was this tsunami warning because it was obvious we'd been hit by something enormous, but all of our sensors were gone, completely gone. If we'd had the capability to get out there, to send disposable drones, just fly out and tell us what you're seeing. We don't care if you crash in the sea, tell us what's there. That would have been marvelous. And I think disaster relief agencies with that type of message is what will help get this technology widely adopted. Governments will have to be dragged kicking and screaming into this era of advanced technology simply because they're concerned about things that are valid. At dinner last night, we came up with questions about things like privacy. Could drones be used to infringe on your privacy? Other people ask, could drones harm you, hurt you, like we see occasionally in the Middle East? The answer is absolutely yes, they could. But so could a tape recorder infringe on your privacy and a fork harm you. The drones aren't the problem. Not really. Our legislation is largely in place to make people behave themselves. But governments are concerned about this new technology, as they always are. It'll be a process of discussion with reputable stakeholders that allows them to feel comfortable. Okay, any other questions? Yeah?
Yeah. What was the cost about advanced drone?
The advanced drone. Yes, it really depends on the technology being utilized. So the advanced drone has a counter-rotating propeller, and the electric engine to do that is pretty expensive, about $500 US. That would push the cost of the drone, well, I mean, pretty expensive, $500, very cheap, but it's about $1,300 for that build. But with a gasoline engine, the price goes way down because the gasoline engines we're looking at, they cost about $120 US. So the target price is $1,000 US per deployable drone. We can't guarantee the price, but that would be what we're aiming to get the component cost with a slight margin for build cost in there. $1,000 per drone is our target, and it's looking very realistic. Remember, a lot of what we're using is really simple technology. I mean, aluminium rails, plastic tubing, a lot of it is very, very simple and stupid technology. It's just we're trying to combine it in smart ways so that you can get these capabilities. Same applies to our radiation sensor. That's a jam jar made of metal. It's a very cheap technology, about $20 per unit in any scale of production. So you can expect the future to be very accessible. $1,000, well, it could still be a lot in some areas of Africa or Southeast Asia. That's true. We can't make it super cheap, because you reach that point where the material cost and the survivability of the technology, you can't go down any further. So let's call it $1,000, and what we'd hope is that in the future it's easy enough for organizations like Red Cross to buy these things and to get them where they're needed, so that the richer countries can underwrite at very low cost for them disaster response in developing countries that is extremely useful. So, any other questions? Oh, one gentleman up there.
Hi. I'm concerned about communications. When you send a plane, I don't know, 300 kilometers away, and it breaks and crashes, how can you get the data? Or
that's a really good question. It depends where it crashes. Simple answer. But yeah, as the plane itself will, in, let's say, the first generation, fly dark. So we envision in the early days, and largely this is due to regulations around the world regarding radio frequency usage, that the planes will be loaded with a flight plan. They will go, and they'll probably come back. And that's what we're doing as step one, because we're well aware that around the world legislation is very different with radio frequencies. So in the US you can use 900 megahertz to speak across, let's say, 10 kilometers or 20 kilometers. In Japan that's completely illegal. So first step, we're not going to do that. They're going to fly dark, And if they go down, you just will have to send some poor sod following the flight plan to eventually find the machine and get the black box and you know, find out that it ran out of battery or gas or whatever, the tail fell off again, whatever. The future, though, is different, and the insane gentleman who built our radiation sensor, Andrew Back, is also working on a concept for communication hubs. And these communication hubs would be deployable throughout a disaster zone to restore ground communication for people, but also for the drones to stay in fairly continuous contact via, let's say, widely accessible things like Wi-Fi. Or GSM communications, because we can also do that. So we're at the early stages of drafting up these communication hubs, which would use things like software-defined radio to fit into the frequencies allowed in different countries, and which would use things like Wi-Fi to restore basic communication for civil areas at very low cost. So in the future, the drones will be in fairly continuous contact with you as they go. And in that case, basically, when it stops talking, you know it's gone down somewhere, and you've got a much smaller search area. We'll have to work out a beacon in the drones so that when they go down, you can find them relatively quickly. That's not been a priority. We've been focusing on basic capabilities, but a beacon should be there, and it won't be that big deal to create. Third generation, just to let you know, we envision, once we're able to build the communication technology on the ground hubs, working on the drones carrying more communication technology and meshing the drones, envisioning that you would always fly quite a few drones, and they would mesh together to be able to create a chain of communication back. And that would change the game entirely, because you could repurpose them at high speed. If one starts to malfunction, you can replace it in the search grid, but you can also watch it go down and then pick it up. You still send that guy out, but he has an easier job. So that's it in a nutshell. Fly dark, fly with greater communication with ground hubs, and eventually have drone-to-drone mesh communication to allow continuous discussion. But it's step by step by step, and that includes waiting for legislation to catch up. We often have the conversation where engineers want to engineer way ahead of what we could legally do. And the answer is no, absolutely not. Because we need to have real-world solutions that will be acceptable. We can't break rules. We can't break laws. We must fit into the laws and still push the boundaries to get us to where we need to go on the communication front. So we are hindered by engineering, but we're also hindered by the fact that legislation means we can't do everything that technology could do yet. So, any final question? Pretty silent in the room. Okay, let's wrap it up. Thank you very much, ladies and gentlemen.
There it is. Yeah, it works. It's still, yeah.